Okay, so welcome back to section 5.2 as we're continuing to this new section where we're going to be talking about what's known as the definite integral. Now, that is a new term, but in reality, what we're going to be doing is just a continuation of the last section, talking about area. Okay, so let's first define what this term is. If you have a function f, so if f is a function defined on some closed interval, we can divide that AB into n what we're going to call subintervals. What a subinterval is it's a smaller interval. So an example was if you have the interval 0, 1, a subinterval of that would be, say, 1/2 to 3/4, because it lies inside this one and it's smaller. So we're going to call these subintervals. Well, first we're going to have the width same as before, b minus a over n. And then we're going to say a is our value x naught. And that's going to be less than x1, less than ... less than xn, which is b. Our endpoints. And what we're going to call x1 star, x2 star, all the way to xn star. Sample points in, so xi star is going to be lie in the interval xi minus 1 comma xi. That's why our index has to start at 0. Okay, so given all this stuff, let's make some space. What we're going to call the definite integral is the thing that we've been working at this point in time, namely the definite integral of f from a to b is, I'm going to use this notation, this elongated s, and then a to b of f of x dx equals the limit as n goes to infinity, sum from I equals 1 to n f xi star delta x. Provided the limit exists, and gives same value for all choice of sample points. And if this exists, then f is integrable on closed AB. Okay, so that's a lot to unpack. So that's basically what we're going to be spending this video on, is trying to unpack what is this definition saying, as well as what's some properties of it. So the first thing that sort of bothers me about this is it's talking about provided the limit exists, same value for all choices of sample points. So let's try to understand that first. Now, the idea with these sample points is, well, if we look at an example like, let's say x squared plus 1 on 0 to 5. Before, what we were doing is we were saying, well, let delta x equal 5 minus 0 over n, or 5 over n. Then we could split up this into 0, 5 over n, 5 over n, 10 over n, all the way to 5 n minus 1 over n, 5. And then when we were computing the area, we were a lot of times, looking at, well, do we want to use the left endpoint? Do we want to use the right endpoint? Do we want to use the midpoint? Do we want to use the lower sum, upper sum? And there was this distinction there. But what this definition of definite integral is saying is this definite integral, which is supposed to correspond to what the true area is really just, okay, within each of these intervals, pick a point. I don't care which point you pick, just pick one. You could pick the left, you could pick the right, you could pick a midpoint, you could pick your favorite point in the interval. Just pick a point. So that's what the sample points are. Is just, okay, pick a point in that interval. But the idea is there's a choice there. There's a choice that you're choosing which point to pick. So how do you know that your choice didn't affect the area? Well, as it turns out, the functions we're going to look at, once you take this limit, the rectangles are getting so small that that choice doesn't matter. As long as this integral exists. Well, when does that integral exist? When does that particular limit exist? Well, if f is continuous, or, well, on AB, so on our interval in question, or has only finitely many jump discontinuities, then f is integrable. Notice that what this is basically saying is that integral, that thing, will exist provided that you don't have an asymptote on this interval. If you have an asymptote, all bets are off. The thing is not going to exist. In fact, because the limit as x goes from the left to the right towards that asymptote is infinity, that area shouldn't be finite. But if there is no asymptote, then your choice of the sample point doesn't matter, and you can find that integral. Okay. So in other words, we can just define the definite integral for the functions that we're going to be looking at this class to just be that limit, and leave off the whole if the limit exists stuff. Now, we have a special term for this. The sum here is called a Riemann sum. It's called a Riemann sum before you take the limits. So before, if we were using the left endpoint, we were calling that a left sum. Right endpoint was called a right sum. If you're just using a sample point and you're not distinguishing what the sample point has to be, it's called a Riemann sum. So to sort of illustrate this idea of choosing sample points, let's compute a Riemann sum. Okay, so evaluate the Riemann sum for f of x equals cosine x plus 1 on 0 is less than or equal to x is less than or equal to 3 pi over 4 for n equals 6. So this is going to be similar to what we were doing last section. We start out with our delta x, and that's going to be 3 pi over 4 minus 0 over 6, or pi over 8. So we can make our intervals 0, pi over 8, and then pi over 8, pi over 4, pi over 4, 3 pi over 8, 3 pi over 8, pi over 2. Each time we're just adding our little bit that we have. Adding our pi over 8 to the left endpoint to get the right endpoint. Okay, so since we're doing a Riemann sum, I'm allowed to choose in each one of these intervals what point do I want to take. And I could just choose left endpoints or right endpoints, but I want to make my life easier so I could choose right endpoints and compute that. That would be the same as my area. So if we call this the Riemann sum, it's going to be pi over 8 times cosine pi over 8 plus 1 plus pi over 8 cosine pi over 4 plus 1 all the way to the last term, pi over 8 cosine 3 pi over 4 plus 1. And you could sum that thing, and that will give you a correct answer for this. It is a Riemann sum with n equals 6. But instead of choosing that, why don't I choose it a little more smart? I know I have the unit circle, right? So why don't I choose values that I know are on the unit circle? This first one, 0 is on the unit circle, 0 degrees. I also have pi over 4, and pi over 4 there, pi over 2, and 3 pi over 4. So I could find now this Riemann sum. It's going to be pi over 8. Cosine of 0 is 1. Plus pi over 4. Cosine of pi over 4 is just square root of 2 over 2. And I do that twice. And then I continue doing those two. And then the last term that I will just put dots to save space is, oh, and here's a plus 1, is cosine of 3 pi over 4 is going to be a negative root 2 over 2 plus 1. Okay. And then you can compute that thing. And what will we get? We'll get approximately 3.02657. And that is a Riemann sum. Now I will say that the actual integral, let me erase this first for space. The actual integral here, 0 to 3 pi over 4 of cosine x plus 1 dx is approximately 3.063301. So, not super far off, but not exactly either. Okay, so that was an example of what with this thing with Riemann sums. Now let's go back to the definition of the integral. So in the definition of the integral, we have this thing. So you have the integral from a to b, f of x dx equals the limit as n goes to infinity, sum from I equals 1 to n, f of xi star, delta x. So when we're looking at this, so far, if you notice, I've been very careful about making sure our functions look something like this. You have function lying above, and you have the area looking like this, so the area was positive. Now, these delta xi's are always going to be positive numbers. That just comes from the formula. If you need to convince yourself, look back at the formula. But what about these values? If I have a function that's lying below the x-axis, and I want to find the area, that's going to be a negative number. So this integral will be negative. So unlike area, the integral can be negative. So that's why the integral is often called a net area. The integral is the area above the x-axis, the positive area, minus the negative area. To illustrate that, let's take this function. So let's say I want to look at the integral from 0 to 3 of this function. So it's, first of all, the area will be this. For the integral will be this value. Notice that if it's lying below the x-axis, it's the portion above, but if it's lying above the x-axis, it's this part. So the integral of this function will be, well, what's the area of this part? Well, that's a triangle. Its height is 1, and its base is 2. So half 1 times 2 minus the area of this triangle. Well, its height is 1, and its base is 1. And you can compute that, that's 1/2. So that's this idea of net area is, in a way, the area below is taking away area from the one above. So that is why this is called net area. Now, this last little bit of time, I'd just like to give you some properties of integrals. These properties won't come into play super incredibly much until next section, but will still help a little bit this section. Okay, so our first property, so let's say properties. Our first property is that if you have a constant, the integral of a constant is the constant times b minus a. And that makes sense if you think about the picture. Constant function, if we want to find from, say, 1 to 2, then it's this rectangle, which is this side length is c, and this is 2 minus 1, or 1. So that particular property does make sense, just going back to the geometry and stuff we talked about last section. Okay, property 2. Well, it's defined in terms of a sum. So if the integral of a sum is the sum of the integrals. You can break them up. It's nice like that. Third property. If we have a constant out front, then that's equal to pulling the constant out. So like, for example, I will tell you that the integral from 0 to 1 of x squared dx is 1/3. So, using this property, the integral from 0 to 1 of 3x squared dx is going to be 3 times this integral, or 1. Okay, property 4. This a to b f of x dx, you can always flip flip the numbers going from A to B to B to A just by introducing a negative sign. That won't be incredibly useful this section, but it will come up next section. Okay, and we have more properties beyond those. Property 5. If you go from A to A of any function, you get 0. Now, why is that true? Well, remember, our width was b minus a over n. But here, b and a are the same, so it's 0. So since our width is 0, all the rectangles have area 0. In a way, what it's asking for is, if I have this function, here's a, what's the area of this line? Well, it's a line, so it doesn't have area. Next property, you can always split up and add up these integrals. The only caveat here is, notice this C has to match with this C, top and bottom. You can't have them flipped, but you could use number 4 to get it that way. This is a way of breaking up integrals of functions that you maybe don't know the integral of yet. Property 7. If you have a function that is non-negative on our interval, then this holds true. Property 8 is similar. If you have two functions and one's greater than the other on the interval, then how do they compare? Well, they compare in the way you want them to. And then the last property is a special case of this. If you have some numbers, little m and capital M, then using property 1, m b minus a, and capital M b minus a bound the integral. And that's all the properties. Now, like I said, a lot of those won't come into play this section, but they'll be useful going forward to next section. So, sorry about this video being a little bit on the longer side, but I wanted to get through all those properties and introduce this idea of integral. We'll be doing a couple examples next time, but I will see you all tomorrow.